Hi Year 12s, welcome back to the 5th video in this series on circular functions. We're now going to turn our attention to graphing sine and cosine as functions of a real variable. And we will also review the terms amplitude and period. So let's get underway. Recall that for a particular angle theta, measured counterclockwise from the positive direction of the x-axis, if we draw a ray from the origin to a point on the circle, making an angle theta, it intersects the circle at the point cos theta for x and sine theta for y. Now what we're going to do is let theta vary. So for each value of theta, as I make my way around this circle, I'll plot a graph showing cos theta, or the x values, versus theta, and I'll plot a graph showing the y values, or sine, versus theta. It's an activity that's often done for students who are sketching trig graphs for the first time. And if you go through this exercise, you get graphs that look like this, like the ones that I've drawn below. And by year 12, you've seen them before, so I'm going to assume that you know them. But I want to make a few comments. Remember that we define sine and cosine using the unit circle, and so the values are going to range from -1 to 1. That's the first observation. And the second observation is if I go around a full revolution of the circle, I end back where I started. And so every time I increase my angle by 2 pi, I don't change anything. So the graphs of sine and cosine are actually going to repeat every 2 pi radians. So although I've only drawn one cycle of this graph, you can think of these graphs as going on forever. This is 1 cycle, 2 cycles, 3 cycles, 4 cycles, and etc. Okay, so they're periodic. They repeat every 2 pi units. And so since they repeat every 2 pi, the graphs are going to end at 2 pi. I like to write coordinates, so I'll say this graph passes through 0, 1 and 2 pi, 1. And for sine theta, it passes through 0, 0 and 2 pi, 0. Now, I think sine is actually the easier one to analyze because it starts at 0. So the y values are 0 at angles of 0, pi, and 2 pi. And the maximum value will occur at pi on 2, giving a value of 1. And the minimum value will occur at 3 pi on 2, giving me a value of -1. Now, for cosine, the halfway point between the halfway point between theta equals 0 and theta equals 2 pi is going to be pi. And a quick check of the unit circle tells us that when I'm at this point here, the x value is -1. So the graph passes through pi, -1, and the halfway point between cosine equals 1 and cosine equals -1 will be at pi on 2 and 3 pi on 2. Okay, so these are standard graphs that we expect you to have memorized or to be able to draw from first principles without notes and without a calculator. All we need to be able to do in this exercise is sketch graphs of sine and cosine, including reflections and dilations. We don't need to worry about translations yet because that will come in a future exercise. So I'll now take a few moments to review amplitude and period, and then we'll quickly do a couple of examples where we sketch some graphs. So let's start with amplitude. Imagine I've got a graph that has a maximum value, a minimum value, and what I'm going to call the mean value or the average value. Excuse me. The mean value is halfway between the minimum and the maximum, and the amplitude could be thought of as either the distance between the mean and the maximum, or the distance between the minimum and the mean. You could also think of it as half the difference between the maximum and the minimum. So to put this in words, I could say it's the mean minus the minimum, or the maximum minus the mean, or half maximum minus minimum. All three of those calculations will give you the same value, and that's the amplitude. Please note that in this context, I'm assuming that the graph is either sine or cos. If you state an amplitude using this calculation for any other function, you're probably not going to be communicating what you intend to other mathematicians, because they will understand amplitude to be, in this specific context, relating to a sine or a cosine graph. Alright, so with that in mind, let's consider a few graphs. So the graph sine theta, by way of reminder, passes through values of 1 and -1. So the distance between the maximum and the mean is 1 minus 0, which gives me 1. Now, if I choose to dilate my graph by a factor of 3 from the x-axis, this time my graph will have a maximum value at 3 and a minimum at -3. And so the amplitude will still be 3. I mean, we'll now change to 3. Now, if I reflect about the x-axis, the graph still has a maximum at 3 and a minimum at -3. And so the amplitude is still going to be 3. Please note, it is not -3. So something that's worth stating here is that the amplitude is always going to be positive. And finally, the fact that I have dilated by a factor of 1/5 from the y-axis doesn't change the maximum or minimum value. The graph is still going to oscillate between -2 and 2. And so the amplitude of the final graph is 2. So in some ways, to find the amplitude, all you need to do is take the size or the magnitude of the number, which is multiplying the sine or the cosine term. Okay, let's talk about period next. So, a formal definition for a periodic function is to say that if it has period capital T, this is a symbol that's often used in physics, if a function f of lowercase t has period capital T, then what I'm saying is if I translate the graph t units to the left or to the right, it actually doesn't matter, I get back to my original graph. And it doesn't matter which value of lowercase t I pick, no matter where I am, if I shift the graph t units, I get back to the original graph. So to make this really precise, I should say for all values t. in the domain of f. But we're assuming that these functions go on forever because they're always repeating, so I'm just going to say for all t. We'll assume that f of t is defined on the real numbers. Note that a graph can have more than one period, but there will always be a smallest period. And that's called in some books the fundamental period, and that's what I'm talking about in this context. So we're concerned with the smallest possible value of capital T. There may be larger ones, but the smallest one, the smallest possible choice, is what I'm going to call the period. So cosine and sine, we've already established that every time I make a full turn around the unit circle, I get back to where I started. So the period there is going to be 2 pi. Now, we haven't actually graphed tan theta yet. In the Cambridge textbook, tan is treated in its own exercise by itself. But if you've done the year 11 course, you will have some recollection that tan theta has a period which is different to 2 pi. It's actually just pi. Tan also has a very different shape. It has asymptotes, unlike the sine and cosine graph, but we'll wait for when that exercise comes. Now, what happens if we change the multiplier of theta inside the brackets? So suppose I dilate my graph by a factor of 1 on n from the y-axis. Before, we had a graph passing like this, ending at 2 pi. If I dilate by a factor of 1 on n, now the graph is going to pass through 2 pi on n for the end of the first cycle. So that means the period has now changed to 2 pi divided by n. And similarly, if I take tan of some number n times theta, the period is going to be pi on n rather than pi. These formulas are not given on exam 1, so I suggest you have this one memorized. You should definitely know that sine and cosine have period 2 pi, and tan has period pi. Alright, once you know how to find amplitude and period, you have the ingredients that you need to sketch a simple trigonometric graph, and in this particular exercise, we just need dilations and reflections and no translations. So, some people find it helpful to start by writing the amplitude and the period down, and for the purposes of this video, I will do that. You'll probably find that with some experience, you no longer need to do this. So let's start by sketching y equals 3 cos 2 theta. So the amplitude is the magnitude of the number, which is multiplying the cosine. In this case, it's 3. Now, the period of cosine of theta is 2 pi. If I dilate by a factor of a half from the y-axis, that's going to reduce my period by a factor of half. So the period is going to be pi instead of 2 pi. And so if I graph 2 cycles, the first cycle will end at pi, and the second cycle will end at 2 pi. I think I'll just write 2 pi and pi. I think that's clear enough. And the graph is going to pass through 3 and minus 3, and you should probably see that I've made an error here. because I drew a sine graph instead of a cosine graph, so I'll change that. My mistake. Cosine will start up here, and then 1 cycle, 2 cycles. Okay, so that's 2 pi for the end of the second cycle and pi for the end of the first cycle, and the graph passes through 3 and minus 3 as the minimum and maximum values. Now, a question that arises is, do we need to label the x-intercepts? I think in this instance, it probably does make sense to do so. So for instructional purposes, I will label them. So remember, the maximum and minimum are sort of spaced halfway between a full period, and the x-intercepts are spaced halfway between the maximum and the minimum. So this first x-intercept is going to be pi on 4. This one is going to be 3 pi on 4. This one's going to be 5 pi on 4. And this last one is going to be 7 pi on 4. It's a bit tedious, I know. Usually in the exam, you get grid paper with the axes already labeled and scaled for you. So the main thing is you understand how to do this, and if you can do it once, you can do it again. The goal is not for you to spend dozens of hours labeling intercepts on graphs that you know how to draw. Okay, so this is just to demonstrate. For the second graph, remember that remember that amplitude is positive. So I'm not going to include the negative sign in the amplitude. The amplitude is simply going to be positive 5. And this time my period is going to be 2 pi divided by 4, which is pi on 2. So this time, just labeling the axes here, this time I will get a sine curve, and remember there's a reflection about the x-axis, so instead of doing this time I need to go the other way. There's 1 cycle, 2 cycles. This is 2 pi, this is pi, and that means this point here is pi on 2, and this point here is 3 pi on 2. And the graph goes through negative 5 and 5. Perhaps you're seeing now why I'm saying the sine graph is easier, because I didn't have to do the halfway calculations the way that I did with the cosine graph. And I've just noticed another error. The period is pi on 2, so I need the graph to end at pi rather than 2 pi, so apologies for that. It is late, but good thing I've picked it up. So the graph ends at pi, the second cycle ends at pi, so the first cycle ends at pi on 2, which means this point here is pi on 4, and this point here is 3 pi on 4. Okay, that's better. All right, I think it's a pretty straightforward exercise. Write down the amplitude and period if you need to, and just be careful about confusing the sine and the cosine graph. Just check before you draw, because you can see I made that mistake in this video as well. So check the sine or cosine, check for a reflection, check your period, and I'll look forward to seeing you in the next video. Thank you.